Scientists of the Albert Einstein Institute are currently preparing a unique experiment in space, LISA Pathfinder. It will pave the way to a new astronomy.
LISA Pathfinder
is a mission to measure perfect rest. However, determining perfect rest is not easy at all when you think about it. Perfect rest compared to what? The best thing to do is to take a second test mass, also perfectly at rest, and measure the relative distance between them.
Scientists want to use this method to measure extremely small length changes caused by gravitational waves. LISA, the laser interferometer space antenna, will probe these ripples in space-time predicted by Einstein with its 3 satellites. LISA Pathfinder will test the free-falling, disturbance-free test masses used in this experiment.
Freeing the test mass from disturbances is so difficult we have to go into space to achieve it.
It is simply too noisy down here on Earth. Man and nature together create a dynamic environment which disturbs measurement on this extremely small scale. That's why scientists are sending LISA Pathfinder to one of the quietest places in the universe. Here, the gravitational attraction of the Sun and Earth cancel each other out.
To measure this state of absolute rest is very difficult. We have to measure the relative distance between the 2 test masses with picometer precision. A picometer is very much smaller than anything we can imagine. For instance, a hair normally grows about 1 millimeter a day. So a hair will grow by 11 nanometers per second, which is about 11,000 times more than what we want to measure here.
To achieve this goal, extensive tests are necessary. LISA Pathfinder is about to reach another significant milestone.
Space missions like this take a long time to prepare, and they have a long lifespan. You start off with an idea. How could you go about measuring this? Then you try it out, go into the lab, build something on your table, check the principle. It won't work exactly like you want it to. But you can see if the idea basically works out, and so on until eventually you reach the exciting phase of building your flight model. It's called a model, but it isn't really a model. It's the real thing which will go into space.
In a Hanover lab, space conditions are simulated. The optical bench is the heart of the LISA Pathfinder experiment. It is assembled in a vacuum tank and connected to the other components of the optical measurement system, the OMS. Its principle is similar to a laser interferometer like the one operated in the GEO 600 Earthbound gravitational wave detector. But the OMS is much smaller and much more complex.
The biggest challenge is that all the different components have to communicate with one another. You can imagine the optical measurement system as being made up of many different small boxes: laser, laser modulator, phase meter, optical bench, the data management unit, DMU. Each one of them works by itself and meets the specifications required of it. But this is the first time that the whole setup has to work together.
And that is just what scientists and engineers are testing here. The engineers work for the space company Astrium. For years, they have been developing programs and procedures to ensure the success of the space experiment. For the last couple of months, they have been putting thousands of commands into the finished components to test how the system works in reality. A mutual familiarization for a successful mission.
If you put together an optical experiment here in the lab, people will be there and watch. The beam is going along here, I have to turn this, adjust a bit, and then you see, okay, it's working all right now. You can press the button and start measuring. In space, you can't do that. The spacecraft has to be self-sufficient. So the optical measurement system checks itself all the time and is smart enough to know what to do when it notices something is wrong. It then automatically changes to a different operational mode or will reboot components so that it can resume normal functions. And that is exactly what is being tested at the moment.
And the system is doing that self-sufficiently too. The closed system cannot be verified with additional equipment diluting the integrity of the responses.
Performance testing is the final highlight. Once we're sure that the experiment will work, we of course also want to know how well it does it. And that's the ultimate test. We run the setup for 10 hours to show that we can achieve a stable precision of 5 picometers per square root of a hertz.
The system achieved this precision at night, alone, and without human assistance.
We know that our optical system is very intelligent. It's met all challenges head-on, and we're very pleased. The spacecraft is also ready and waiting. There are only a few obstacles left before launch.